Okay guys, so we are finally to part 3 where we are actually going to construct a hypothesis test on our own, right? Now that we know the ideas behind the hypotheses, the p-value, and how we make a conclusion based on that p-value, we're actually going to figure out how did they get that p-value in the first place. Okay, so in part 1, we used a simulation to estimate a p-value. That's not how we'll do it from now on. To decide whether or not Mrs. Bakula was exaggerating about her free throw percentage. Today, or right now, we will use a formula to actually find the real p-value. So we're going to carry out the significance test from part 1 again, begin by writing the hypotheses. And we already kind of sketched these out in the first part when I went back over it. So the null hypothesis is that my true proportion of free throws made, P, is equal to 0.8, right? We're assuming that I actually am an 80% free throw shooter. On the other hand, the alternative would be that I'm not an 80% free throw shooter, except I'm not thinking that I'm better than that. I'm thinking that I'm worse, so that P is less than 0.8. And of course, I have to state what P represents. So where P, again, is the true proportion of free throws made by me, Mrs. Bakula. Okay, and then I also have to state my significance level. I don't have an argument for one of the other, the type errors being more significant, so I'm just going to go with 0.05. That's pretty standard. Okay, so number 2 has 2 parts. It says A, each class would have found a different p-value because each dot plot would have been different. Now this is if we really had done that simulation with the spinners, we'd been in class, I'd been able to collect the data from each of you. Each class would have had different dot plots. So the estimation for the p-value would have been a little bit different, right? Some classes might have had 3 dots less than 0.64, some only 1. So we don't want to have something that changes from simulation to simulation. So instead, let's think, would it be appropriate to use a normal distribution instead to model the sampling distribution of p hat? Well, if we look back, I pointed this out then, that sample distribution looks approximately normal, right? So let's see, we have some conditions we have to check in order for that to be the case. If you remember back from our confidence intervals, in order to use a normal model to model the sampling distribution of p hat, we checked large counts. This justified using a normal model. So if you remember large counts, it was that n times p, which for us, n is those 50 free throws that I shot, times p. Now this is different from confidence intervals. I actually know what I think p is versus the confidence intervals where I was trying to estimate that. So I use actually p, not p hat. So 50 this time times 0.8. So let's see, what would 80% of 50 be? 0.8 times 50 is 40. Okay, we have to check that that is greater than or equal to 5, which it is. And then we have to check the n times q. So n times the proportion of misses, which if the proportion of makes is 0.8, the proportion of misses is 0.2, right? 1 minus 0.8 is 0.2. And of course, if 40 of them were makes, then 10 of them must be misses. I could multiply this out, but I would get 10. And that's greater than or equal to 5. So the large counts condition is met. Then B is, are there any other conditions we should check? Of course there are. Just like with confidence intervals, we have to check the random sample condition. So can we consider those 50 free throws that I shot a random sample? I think that's fair to consider them a random sample of all the free throw shots that I will ever make. You might be thinking, well, what if, that day, I don't know, your wrist hurt and that made, affected your shots. You're right, but for the purposes of this example, we're going to assume it's a random sample. And then the other condition we have to check is the 10% condition. So that's that our sample size, n equal to 50, is less than 1/10 of the population. So if you remember, the population was all free throws. I'm going to abbreviate. Mrs. Bakula could shoot. All the possible free throws that I could shoot. And 50 is definitely less than 1/10 of that, right? I could shoot a lot of free throws. Okay, so now that the conditions have been met, and notice those conditions are really similar to the ones for confidence intervals, we're going to find the mean and standard deviation of the sampling distribution of p hat. Now, before, we only had to find the standard deviation because it was part of the margin of error. We actually ended up finding the standard error because we didn't actually know the population proportion. We had to use the sample proportion to estimate it. So now I'm actually going to give you these formulas, and I can hear it in my head right now. Someone in the class is, imaginarily raising their hand and thinking, where are these formulas coming from? And I hear you, I understand that. I am giving them to you, right? I'm defining them for you. If you really do want to know, you can look back at section 6.4, right? This is all from section 6.4 on the sampling distribution for sample proportions, but I'm not going to go into why they are true necessarily. Okay, so here they are. The mean we call mu sub p hat. We haven't seen that one yet, but this is the mean for the sampling distribution of sample proportions. It is equal to p. Right, easy enough. It's similar to how the mean for sample means is just equal to the population mean. The mean for sample proportions is just equal to the population proportion, which for us in this case, we're assuming is 0.08. Then the standard deviation, we have seen this formula before, sigma sub p hat. Okay, it is equal to the square root of p times q divided by n. Now, when we use this for confidence intervals, again, we put in p hat and q hat because we didn't know p and thus didn't know q. But now we know p, or we're assuming it is 0.8, which makes q 0.2, and the n in this case is 50. And then we take the square root of all of that. Okay, so let's calculate that one. We have second square root of 0.8 times 0.2 divided by 50. Hit enter, and I get 0.0565. I'm going to round to 3 decimal places, so that would give me 0.057. 0.057. Okay? All right. So now that we have the mean and standard deviation, we can label the normal curve. Okay? Label the normal curve. So my mean goes in the middle. That's my population proportion, I'm assuming. So that's 0.8. And then I need to add a standard deviation to 0.8 to get one standard deviation above the mean, and I'll actually do that 3 times. So I'm gonna go ahead and do that. 0.8 plus 0.057 plus 0.057 plus 0.057. Okay, so those are my 3 standard deviations above the mean. I'm gonna write those out. It was 0.857 and then 0.914. and then 0.971. Okay, now I have to get the standard deviations beneath the mean, so 0.8 minus 0.057, again and again. Okay, so I get 0.743 is 1 standard deviation beneath the mean, 0.743, and then 0.686, and then finally 3 standard deviations beneath the mean is 0.629. Whew, okay, so I really want to point out, because some of you have been making this mistake in your chapter 6 homework, this is the normal curve with a mean of 0.8 and the standard deviation based on this sampling distribution. So it's 0.057. Okay, so how many standard deviations below the mean, which standard deviations below the mean, that's a z-score, is p hat equal to 0.64. Now, normally I would say from the mean, but I specifically said below because I can tell 0.64 is less than 0.8. Okay, so let's calculate this z-score. Well, I'm gonna kind of state a new way to think about it in terms of words. Different from that value minus the mean divided by the standard deviation. Instead of saying value, I'm going to talk about my statistic, my stat. And then instead of saying mean, I'm going to say minus the parameter, because the mean is equal to that population parameter, p, divided by the standard deviation. Now this new way in words for us, of course, I'm also calling z here the test statistic. You'll see that come up later. This new way in words is going to work for hypothesis tests for means too. The stat and the parameter will be different, but this way for we say it in words works as well. Okay, so that's my general formula. Now the statistic I'm talking about is p hat. Its parameter is p, which again is the mean of the sampling distribution for p hat. Then I divide by the standard deviation. So the sigma sub p hat, which is the square root of p times q divided by n. Okay, and then I just fill into that. So I have 0.64 is my value for p hat. I'm assuming p is 0.8, and then I divide by, again, it's p, so 0.8 times 0.2 divided by 50 and take the square root of all of that. Okay, I can type this as one string into my calculator to get my result, so I'm going to do that now. I'm going to type in parentheses for the top. So just sketch those in, parentheses, 0.64 minus 0.8, because I want that to happen first. And then divide by the second square root of 0.8 times 0.2 divided by 50. Now, I know we already calculated this and we rounded it to 0.057, but I want to try to avoid rounding error as much as possible, so I'm going to use the full version here. Okay, if I hit enter, I get negative 2.828. Now remember, this is a z-score. I'm going to use table A next, and table A only has 2 decimal places, so I'm going to round to negative 2.83. Okay, so z is negative 2.83. And then it says, find the probability of an 80% shooter making 32 out of 50. Oh, I really meant for this to be up here. 32 out of 50 is a p hat equal to 0.64 or less. Okay, so I know that z is equal to negative 2.83. If I look at table, put a comma there. If I look at table A2, this should be A2, I can find the probability, which remember is a left area. I could sketch it over here. Excuse me, 0.64 is going to fall about between 0.629 and 0.686, somewhere in there, right? So maybe I'll put this in green. So I'm going to fall somewhere in here, and I'm looking for the probability of getting a sample proportion of that or less. So I'm looking for this tiny little left area here. And good thing it's a left area, because that makes looking at table A much easier. And I just realized I forgot to get my table A out, sorry. Okay, so we are going to look at our table A. And of course, I'm going to look at the negative z-score side because I have a negative z-score. So I find negative 2.8, and I go over to 0.03. So negative 2.83 gives me a left area of 0.0023. Okay, so my probability is 0.0023. There we go. Okay, so we have our p-value. That's my probability of getting a sample proportion of 0.64 or less purely by chance when the true proportion is really 0.8. Now, 0.003 is really small. So I'm already thinking about what my conclusion is going to be, but let me just make it really clear. The p-value here is 0.0023. Okay, that probability I just calculated, that's my p-value. So my conclusion then is, since my p-value equal to 0.0023 is less than alpha, right? 0.0023 is definitely less than alpha equal to 0.05. We reject the null. Okay, anytime your p-value is less than alpha, you reject the null. But then I have to explain what that means in context. So it means we do have convincing evidence that Mrs. Bakula, I could say, is not an 80% free throw shooter, but I'm going to phrase it as affirming the alternative hypothesis that I am less than an 80% free throw shooter. So Mrs. Bakula is less than an 80% free throw shooter. Okay, done. We have completed our first ever full hypothesis test. So on the next page in the big ideas, I'm going to talk to you about the 4-step process. And guess what? We have a 4-step process for hypothesis tests too. The good news is it fits those same 4 steps. Here was what we stated, right? The hypotheses and alpha. What we state is a little bit different, but having to state something is the same. We also have to state that what the parameter stands for. And then step 2 was where we did the planning stage and we checked the conditions. Good news here is that checking the conditions is very, very similar than it was for confidence intervals. And then we actually have to do, right? We have to calculate. So we had our general formula with our specific formula. We plugged the numbers in and we got a value. This is what you have to show for the do step. And also, you have to draw the picture, right? I told you that wasn't going away. You still have to draw this normal curve whenever you make this calculation. So once we have our do step, part of the do step is also finding the p-value. And I just want to point out that this p-value is the probability that p hat is less than 0.64. Before, we would have said the probability that some value x is less than another value, and then we would have looked at the normal curve. But remember, this normal curve represents sample proportions. So we say the probability that p hat is less than 0.64. And then the final step is to conclude, which is what we did in number 7. Okay, so remember, those are our 4 steps: state, plan, do, and conclude. So we will phrase that in our big ideas on the next page.